I'm Christian Root Bowman. I'm going to be reviewing molecular orbital diagrams and some information about molecular orbitals in general. Here we're presented with a particular molecular orbital diagram. These molecular orbital diagrams, we're going to generally be using them for homonuclear diatomic elements. So homonuclear, it's the same species, diatomic, there's two of them. In this particular example, it's going to be a diagram that applies specifically to B2, C2, and N2. Once we get to oxygen, the diagram is slightly different because the energy is a little bit different. We won't get into why, and on an exam, you'll be presented with the proper diagram to use. So we're asked to fill in this diagram for B2 specifically, and then once we have this molecular orbital filled out, we're asked to interpret it. We're asked about bond order, stability, magnetism, and then we're asked to compare the stability of some different ions of B2. So first, we have to establish the atomic orbitals. We build our molecular orbitals off of our relative atomic orbitals. So let's go ahead and do our atomic orbital for boron specifically. So looking at the periodic table here, let's go ahead and find boron. There it is. And the atomic orbital, we're only interested in the valence electrons here. Valence electrons are going to be the electrons that are participating in bonding. So when we're talking about a molecular orbital, we're talking about how bonding happens, what's going on with bonding. So we're really only interested in those valence electrons. So boron's in the second period. So I know that my N is going to equal 2. That tells me about the relative size of the orbital. There is my S orbitals. S is going to tell me about the relative shape of my orbital. And then I've got my P orbitals over here, again, also telling me about shape. So I've got 2S and 2P. I can see there I've got two different 2S orbitals and one 2P orbital. So let's go back to our diagram and let's just fill those in. There's our two 2S orbitals and our electrons, and our one 2P electron. It's homonuclear and diatomic, so the valence electrons for the other boron are going to be exactly the same. Okay, so that part is done. My atomic orbitals for boron are done. It was pretty simple. Now at this point, I'm going to start filling in my molecular orbitals, and I'm going to be pulling electrons from both of my atomic orbitals. The really nice thing is the exact same rules for filling atomic orbitals with my electrons apply also to my molecular orbitals. So I'm just going to start with my lowest energy, filling in electrons. I'm going to go up. So the first one is a sigma 2s molecular orbital. Grant that our molecular orbitals are different than our atomic orbitals, right? So we want to say it's a sigma 2s molecular orbital specifically. And then we go up and we've got that sigma 2s antibonding molecular orbital. And then finally, these two unpaired electrons in this pi 2p bonding orbital. You can see on the diagram there, bonding and antibonding are denoted by the presence or absence of a star. The antibonding orbitals have that little star on there. Okay, so we're done with that first part. And that same procedure, finding my valence electrons, filling in my atomic orbitals, and then filling in the blended molecular orbitals, that'll apply to any of my homonuclear diatomic elements. So that part is done. Now we need to interpret this. So bond order is simply the number of bonding electrons minus antibonding electrons divided by 2. This is going to give us a notion of how many electrons are stabilizing this molecule in bonding orbitals and how many are destabilizing it in antibonding orbitals. So the higher our bond order, the more electrons we have in bonding orbitals and the more stable our molecule is going to be. So there's our formula for bond order. For this particular molecule, we have 4 electrons in bonding orbitals, 2 in the sigma 2s bonding orbital, and 1 in each of the pi 2p bonding orbitals. And then we've got 2 electrons in that sigma 2s antibonding orbital. So our overall bond order is 1. A non-zero bond order is considered to be stable. So in this case, our bond order is 1. So it is a stable molecule. Magnetism, paramagnetism, diamagnetism, it asks us if we were to place this molecule in a magnetic field, how would it respond? just looking at, say, the Lewis structure is not enough, because what we really need to know is, are there unpaired electrons in this molecule? Because it's those unpaired electrons which have charge that are going to respond to the magnetic field. So looking at our molecular orbital diagram, we've got two unpaired electrons. We would expect those to interact with the magnetic field, and sure enough they do, so we consider this paramagnetic. Finally, we're asked here, which is most stable, B2, B2, 2 plus, or B2, 2 minus? So with 2 plus, we're losing 2 electrons. With 2 minus, B2, 2 minus, we're gaining 2 electrons. You can look at our molecular orbital here. Our rules for taking away or adding electrons are pretty consistent. It's just reversed when we're taking them away. So if we were to take away 2 electrons, they would both come out of that pi 2p bonding orbital. So we're losing electrons from a bonding orbital. Our bond order is going to go from 1 to 0, which is going to destabilize this molecule. With B2, 2 minus, we're going to add both of those electrons to that same bonding orbital, the pi 2p. So in fact, our bond order is going to be higher. It's going to be 2 for that B2, 2 minus. So it's going to be more stable. And when it's more stable, when we have more electrons in bonding orbitals, it's actually going to decrease the length of our bond. It's going to be a shorter bond. It's going to be a more stable molecule overall. I hope this has been a useful review for you of how to fill in molecular orbital diagrams and then how to interpret those to answer questions about bond order, stability, and magnetism.